let's continue our discussion of categorical data analysis with the chi-square test of independence. Now, the data that I will be working with is from the Haynes, a Health and Nutrition Examination Survey from 1976 to 1980, in which the Public Health Service examined a representative cross-section of a little over 20,000 Americans ages 1 to 74. The goal was to obtain baseline data regarding such things as demographic variables, such as age, education, income, psychological variables such as, or physiological variables such as weight, cholesterol levels, and prevalence of different diseases. Now, one of the variables that they worked with was handedness, whether somebody was right-handed or left-handed or ambidextrous. They took a subset of a little over 2,237 Americans, specifically in the 25 to 34 age group, from this sample of 20,000 plus, and they looked at the handedness. Now, the question is there evidence to suggest there's a difference in handedness between gender? So that's like saying, is handedness and gender independent of each other? If they're independent of each other, then knowing one doesn't tell us anything about the other. If they're dependent, then there's a connection, meaning there's a difference between handedness based on gender. All right, now, to look at this data, one of the things you might want to do, it's not a requirement of the process, but just in terms of the thought process, what if I convert each of these into proportions? So 87.54% of the men surveyed was right-handed, whereas 91.45% of the women surveyed was right-handed. So based on the data, it appears as though that women have a higher prevalence of being right-handed as do men. Left-handed, it appears just the opposite, that men have a higher percentage of left-handedness, and it looks like men have a higher level of being ambidextrous as compared to women. But does the data actually suggest this is reasonable, or are the rows in the columns, the handedness and the gender, independent of each other? So for my null hypothesis, I'm going to state that handedness and gender are independent. Handedness is my row variable, and gender is my column variable. So generically, it'd be saying rows are independent of columns. Specifically for this example, handedness is independent of gender. And then the alternative hypothesis would be that there's a connection between handedness and gender, which suggests that handedness and gender are dependent. Okay, now what I need to do is I need to enter my original data. I'm going to jump back to right here. I need to enter that in my calculator so that I can actually do the analysis. Now, the assumptions here are going to be the exact same as what they were earlier. It's a chi-squared test. Each of these has to be in a independent and so forth. It's count data. Has to meet the qualification for multinomial experiment, where each observation falls into only one of the column variables, either a man or a woman, and only one of the row variables. So if somebody's right-handed, they're not also ambidextrous. Ambidextrous says they can use both hands. So what I'm going to do is go to my calculator, and I need to enter this data in a matrix. So I will do the second matrix, and I need to put it into matrix A. So I'm going to go to Edit, and then Matrix A. Now, switch back to the computer real quick, and take a look at this. This has 3 rows and 2 columns. So this matrix is a 3 by 2 matrix. Whoops, matrix. Kind of messed that up. Let me fix that. Matrix. There we go. I need that information so when I go to the calculator that I make sure the matrix I set up conforms to what I actually have. So going back to the calculator, it's 3 rows by 2 columns, so it's 3, enter. I need to change that to a 2. I mean, who knows what you may have in your calculator. You can see values here based on the last time I put something in a matrix for something totally different. Hit enter, and this is going to change this to be a 3 by 2. See, there's 1, 2, 3 rows, 2 columns. Now, I'm going to put my data in there based on what I have on a screen. So there's 934, 1070, 113, 92, 20, and 8. That's the observed matrix. I'll hit second quit to get out of there. Go to Stat, Tests. I will hit the up arrow key because I know it's on the bottom, and right there, option C, that is my chi-squared test. Now this chi-squared test is only the test of independence. It will not do goodness of fit. For the goodness of fit, you need to do it by hand or use a computer program that we wrote. All right, so I'll select it, and now you know why I put the observed value matrix A. That's where the program is expecting it. Yes, I can change that matrix name. I can put it in a different matrix if I want, but I don't want to mess with it. I want to leave it the way it was. Expected values, matrix B. Well, what that is saying is the calculator is going to compute the expected values for you and put it into matrix B. Remember, the expected values are actually part of our assumptions. I can't address that part until I actually run the test in this case, because running the test will calculate the expected values for me. I could do it by hand, but I don't want to. So I hit calculate, and there's some information that I'm going to want to keep. Go back to my computer screen now, and I'm going to jot this down. Although it's not going to be of great use to me, chi-squared is 11.8061. That's the test statistic. Really what I'm interested in is the p-value, 0.0027. So based on this p-value, I'd reject and say that there is a connection between handedness and gender if the assumptions are satisfied. So I need to address the expected values now. All right, if I switch back to the calculator, I'll clear that. I'll go back to matrix. And you can do this a couple of ways. If I just select matrix B, hit enter again, there it is. And I can scoot back and forth with my right and left arrow keys. Now what I expect my students to do is to copy these down and show me the expected value matrix. Identify it and state how you know that the assumptions are satisfied. Look at these expected values. They are all greater than 5. So you remember what we have to show is that none of them are less than 1, and no more than 20% are less than 5. Well, if they're all greater than 5, then clearly the assumptions are satisfied. The other thing I could have done is gone to matrix, edit matrix B. When I do, there's my values. So they show up nice and neat. All right, switching back now to the computer, I'm going to say, hey, there's my expected values, the expected value matrix. They're all greater than 5. So my assumptions are okay. And now I'm going to say, yeah, there does appear to be a connection between handedness and gender based on that p-value. Okay, that's it for test of independence. The key thing is count data into multiple categories now. I have multiple row categories, multiple column categories. I actually have 2 variables. Goodness of fit, there's 1 variable, multiple levels. Test of independence, there's 2 variables, multiple levels. So it's checking to see if there's a connection between the column or the row variable and the column variable. That's what this is all about. All right, that's it.